Okay, we've made it to section C3 in the appendix. This is all before we learn any calculus. This is just the fundamentals. This is pre-calculus, really, to make sure that when we do get to these trig functions, that you're ready to go and ready to use them. Now, there are 6 trig functions, 3 that are very familiar to you, sine, cosine, and tangent, and then the less familiar that are used that often, maybe cosecant, secant, cotangent. Those 3 are always easily derived by simply taking the reciprocal of sine, cosine, and tangent. So if we know the sine value, I can get cosecant pretty readily by doing 1 divided by the sine value. Just flip it upside down, whatever that value is, you've got your cosecant. First thing I'd like to do is establish the value of those trig ratios based on a right triangle. So let's get started by looking at a right triangle and finding out, well, why we even call them ratios. They are functions of angles, but we also call them ratios. So this is section C3. And the first thing to do is define the trig functions, or trig ratios. And the first set of definitions are for acute angles only. Acute angles are angles that are between 0 and 90 degrees. Those are acute angles. Think of the word cute. It's small. Okay, between 0 and 90 means it'll fit inside of a right triangle. So let me draw a right triangle, a nice vertical side over here, a nice horizontal side down here. And let's connect the dots over there, because that is where my angle goes. And that angle must be between 0 and 90. It cannot be 0, it cannot exceed 90, because there's already a 90-degree angle right here. This one's 90. There's my angle, theta, right there. The definition, at least of the more important fundamental trig functions, the top 3 being sine, cosine, and tangent, have more to do with the sides of the triangle almost than the angle. Now, if you were to put your eyeball here, imagine your eye is staring across. We would say we're staring across at the opposite side of the triangle. Right here, next door neighbor is our adjacent side of the triangle, and the longest side is referred to as the hypotenuse side of the triangle. Now, the trig ratios of this angle have everything to do with these 3 sides, but the sine has been defined as the opposite side divided by the hypotenuse side. The cosine has been defined as the adjacent side divided by the hypotenuse side. And the tangent has been defined as the opposite side divided by the adjacent side. And you might remember a quick way to remember these 3. It's SOHCAHTOA. That's the quick way to remember those. So let me give you an example of finding these 3 trig functions or ratios given some information on the triangle. This is why we call them ratios, by the way. The word ratio means rational, means fraction. So these are fractions. And also, if you look carefully, you're going to notice that the trig ratios are unitless. Not because they're in radians. The theta inside can be in degrees or radians. That doesn't matter. I'm talking the output for sine and cosine is a number, and that's it. There is or are no units. Because if this opposite were in inches, the hypotenuse were in inches, the inches cancel, no units left. Let's try one. So I'm going to give you a triangle here, and let's make this 2 units long. Might as well make this one 2 units long, too. We'll make it interesting here. And I'm not going to tell you the hypotenuse. Well, for that, we're going to need the Pythagorean theorem. A squared plus B squared is C squared. So this is my A, this is my B, and let's go ahead and discover what C should be for this triangle. And by the way, theta will be right here. So A squared will be 2 squared. b squared will also be 2 squared, and we don't know c squared just yet. 4 and 4 make 8. So c squared is actually 8. And therefore c itself is the square root of 8. Don't leave a square root if there's a perfect square hiding in there. So go ahead and let's factor that out. 4 times 2. Each one gets their own square root. And it's 2 square roots of 2. Now I can go up here and label that. All right, guys, nobody knows the angle yet, but I certainly know the sine, cosine, and tangent. So let's do it. Sine of theta, with no information on the angle at all, is supposed to be the opposite side divided by the hypotenuse side, which would be the opposite side divided by the hypotenuse side. You notice the 2's cancel, and I get 1 over radical 2, but, well, we're not really supposed to leave a radical in the denominator, so let's go ahead and rationalize it. So I get square root of 2 over 2, and that is my sine of my angle. Now, it turns out that if we did cosine, not a lot's going to change on this particular problem because that's adjacent over hypotenuse. And my adjacent side right next door is also 2. The hypotenuse remains 2 square roots of 2. The 2's cancel as before. And actually, looks like I'm getting the same answer. That doesn't always happen. And finally, let's do tangent. The tangent of this unknown theta is supposed to be the opposite side over the adjacent side. The opposite side is, well, let's go back to the picture and stare across at the 2. The adjacent side is right next door, also a 2, and I believe we're done. It's 1. Now, I know you're looking at this thinking, actually, I think I do know the angle. There's only one angle that's going to get these sides to be the same like that. An isosceles triangle where the sides match. That means that the angles need to match. So actually, it turns out that these thetas are the same. And if these thetas have to add up to 90, 90 over 2 is 45. So this must be a 45-degree angle. So now we know the sine, cosine, and tangent of 45 degrees, and we got it using a triangle. We got it using the Pythagorean theorem. Now, if we need the other trig functions, we can get those by doing the reciprocal. So let's define those other 3. The other 3 trig functions are cosecant, which is 1 divided by the sine of the angle, secant, which is 1 divided by the cosine of the angle, and finally cotangent, which is 1 divided by the tangent of the angle. Let's try that for this example. Now, the cosecant of 45, in this case, must be 1 over the sine of 45, which is 1 over that. Now, 1 over means reciprocal, so all you really need to do is turn it upside down, but we never leave a radical in the denominator. So actually, the answer is this. 2 square roots of 2 over the square root of 4, which is 2. So the answer is simply square root of 2. So you know the same is going to happen for cosine since the values are the same. But tangent, 1 over the tangent of 1 is 1, so that didn't change very much at all. So you're able to get secant, cosecant, and cotangent pretty readily by just doing the reciprocal 1 over. Okay. Now, there are other ways to define the trig functions. There are other ways to define the trig functions using a circle, and it works for any angle, not just acute angles. So we need to look at that definition as well. So let's take a look at that. So the trig functions have been defined using SOHCAHTOA, but also, what about bigger angles? Angles larger than 90. Or negative angles, for that matter. So let's take a look at a way of figuring out the sine, cosine, and tangent of those angles. So this will be trig functions of any angle. So let's say, for example, We draw a circle. Got our circle here. And we open up an angle that's this big. Now, there's just no way you're going to fit that inside of a right triangle. However, you know your radius. And I'll also maybe help you get the location of this point x comma y. In fact, I might even tell you the location of that point. It turns out that you can now define the three trig ratios as follows. The sine of theta, the big theta here, is the y value over the r value. The cosine of the big angle theta is the x value over the r value. And by the way, x and y can be negative. In this case, in fact, they're both negative in quadrant 3 over here. And then finally, the tangent of theta is the y value divided by the x value. Now, if you forget these definitions, if you forget those definitions on the circle for the larger angles, I have a great way that helps you remember those definitions. And here's what I want to take a look at. If you take a close look at this circle, you can form a right triangle, but I want you to do it by drawing a vertical line, not a horizontal line, a vertical line. So don't do it over here. Now, if you do that, what you're going to find is a nice little right triangle parked in the corner here, and it will have an acute angle right there, and this acute angle will be theta prime. Now, we call theta prime the reference angle. So let's say for the moment that instead of getting the sine, cosine, and tangent of the big angle theta, why don't we do it for the reference angle? Now, y is the vertical direction of how far we are from the number line. So I can draw that side and label it y. X is how far to the left or right we are from the origin, and I can label this side x. So believe it or not, you can use SOHCAHTOA. So the sine of the big angle theta is very much related to the sine of the little reference angle. So let's do the sine of the reference angle using SOHCAHTOA. The sine of theta is opposite y divided by hypotenuse r. And that's what I have over here. Let's go back and do the cosine of the little reference angle. That would be adjacent x over hypotenuse r, which is what I have over here, x over r. And finally, the tangent of theta prime is opposite y over adjacent x. There it is, y over x. So I've given you a great way to recreate those formulas should you ever need to do that. Also, take a very close look at this little triangle here, and you should realize that x squared plus y squared should be equal to r squared if the Pythagorean theorem says so. And that means that if you're ever missing the radius, you can always compute it as the square root of x squared plus y squared. So now I'm going to give you an example. I'm going to give you the coordinate. So the angle, we'll open it up. We'll have the terminal ray touch the circle, and I'll just tell you what the coordinate is. And from there, we should be able to get the sine, cosine, and tangent. So again, let's draw a circle here. I'm not going to indicate what the radius is, but I'll draw a circle. We'll open up an angle. Let's make it big. We'll bring it all the way over here and stop it right there, and I will tell you what this location is. This location is, it's got to be positive x, so let's make it 2. It's got to be negative y. Let's make that negative 3, and that's all you get. So your job is to establish sine, cosine, and tangent. But wait a second. Don't you need r? That's right here. But we just came up with a formula for r. It's r equals the square root of x squared plus y squared. So let's find out what r truly is. 2 squared plus y squared. Everything's positive in there. Negative number squared is positive. And it's not a very friendly radius, but that's what it is. So we should be able to jump to sine, cosine, and tangent relatively quickly. Y over r, x over r, y over x. X over r, y over x. So we've got our tangent minus 1.5, but these, yeah, we shouldn't leave those radicals down below, so let's do some cleanup on that. Both of them need to be rationalized. Square root of 13. So here it is, minus 3 square roots of 13 over 13. That's my sine. This is going to be 2 square roots of 13 over 13. That's my cosine. And then minus 3/2 or minus 1.5 is my tangent. So as you see, you can do the sine, cosine, and tangent of any angle. All you need is the point or a point on the terminal ray on the circle. By the way, that theta could be large, it could be negative, it could be, we could have taken 3 or 4 trips around the circle. Turns out the trig functions don't even care what the angle is. It simply cares where the terminal side rests. So that angle could have been, let's say, 300 degrees, or this angle could have been 300. It kind of looks like 300. Or it could have been 360 plus 300. So 660 degrees is a full trip around the circle and another 300 degrees, bringing the terminal side here. So that's something very important to note, and that is the trig functions of coterminal angles are identical. So it's just based on where the terminal side is. I'm going to finish up with the unit circle. So let me find my unit circle here, because there is a lot of value in this unit circle. So I want you to take a look at the unit circle here. It's a great way to find the sine, cosine, and tangent of a variety of angles. What they've done on the unit circle is they've given you all of these little magic x, y coordinates on all of these very interesting angles right here. Notice they're listing the angles in degrees and radians. So let's say, for example, I wanted to know what the sine, cosine, and tangent of 135 degrees was. We could draw in our angle theta and simply go here and pick up our x and our y. Now, something very interesting is about to happen. The sine of theta that used to be defined as y over r just became y. The cosine of theta that used to be defined as x over r is just x. And the tangent of theta remains unchanged, and it's y over x. Now, why did I get rid of the r? Think about it. Didn't get rid of the r. It's called a unit circle, meaning radius is 1. So what's the sine of 135 degrees in this case? So we can cross this off and put 135 degrees, and we can read off the y value, and we're done. What's the cosine of 135 degrees? Simply read off the x value, and we're done. And then what's the tangent of 135 degrees? Do your y over x. So that would be square root of 2 over 2 divided by minus square root of 2 over 2, which is negative 1. See, unit circle is very valuable in terms of obtaining the values of sine, cosine, and tangent for these common angles. Now, the last thing I'm going to leave you with is I do want you to know the sine, cosine, and tangent of 5 special angles. It's going to really help when we start solving trig equations to know these off the top of your head. For instance, sine of 30 degrees is a half. The cosine of 30 degrees, square root of 3 over 2. The sine and cosine of 45 degrees, square root of 2 over 2. And the tangent of 45 is 1. It's nice to know those by memory, but what if you forget them? Now, the thing is, your calculator can't reveal that to you. They can't reveal the exact answer necessarily. If you did the sine, let's say the cosine of 30 degrees, your calculator is going to say 0.866 and more decimals. What it really means is a square root of 3 over 2. And I want you to know that exact answer, and it plays a role later when we solve equations. So how do we remember all that? I have a wonderful table that will help you remember that. So the 5 common angles I'm interested in are 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. And I want you to know the sine, cosine, and tangent of all 5 of these by memory. Also in radians, this is 0 radians. That's pi over 6 radians, pi over 4 radians, pi over 3, and pi over 2 radians. You really want to know if those are correct? Replace pi with 180. Over 6 is 30. 180 over 4 is 45. 180 over 2 is 90. Now, on the left side, I want you to put sine and cosine. And then a big, huge square root symbol, like that. And under that, a big divide by 2, entirely divide by 2. And now, just count. Start at 0 and count up. 1, 2, 3, and 4. Now start at 4 and count backwards. 3, 2, 1, and 0. This is really the best table I've seen in terms of remembering the sine and cosine of the various angles. So let's do a few. Sine of 30 degrees. Remember I said I had that memorized as 1/2? We'll line it up. Sine of 30 is right here. It's a square root of 1, because it lives under a square root, all over 2. Which is 1/2. We don't need the square root for that. Remember 45? We worked on that earlier. The sine of 45 degrees is, line it up, square root of 2 all over the 2. And you remember we got that value earlier. Let's do the cosine of, let's do 30 degrees. Cosine of 30, line it up. Square root of 3 over 2. And we're done. That's already in simplest radical form. What about tangent? Now, tangent can be constructed as sine over cosine. So let's do the tangent of, how about 30 degrees? The sine of 30 degrees is right here. We did it already. Square root of 1 over 2, that's 1/2. The cosine of 30 degrees, we did that already. It's right here, square root of 3 over 2. By the way, do you notice that they both have divide by 2? So you know what? We don't even need the divide by 2. So if we do this again, tangent of 30 looks like this. Sine, square root of 1. Cosine, square root of 3. You don't even need the divide by 2. So I get 1 over radical 3, and we do some cleanup here, and we get square root of 3 over 3. And that indeed is the tangent of 30 degrees. So if you're looking for the best way possible for remembering the sine, cosine, and tangent of those 5 common angles, I really think that's it. And you can write that table down, but don't use it as a crutch. You really want to start learning those and remembering them if you haven't done so already. Okay, so that's the end of this video. The next video, we're going to talk about trig identities and solving trig equations. So we'll see you in the next video.